Hello, my name is Christopher, and I'm from Team 9415 Wrench Dressing, and welcome to my tutorial on how to make parametric herringbone gears. Let's start off. We're looking at a design that's on our robot this year that uses these parametric herringbone gears. Parametric means that we can determine multiple parameters and like the size, number of teeth, how much they twist, and all that. And we can generate those and 3D print them to be very highly customized gears. They're herringbone gears, which is this shape as you can see here. This has a variety of benefits. They mesh together like this, arrows pointing towards each other or arrows pointing away. And these benefits include they self-align themselves. So even if you have a loose set screw or something like that, they will stay in line. They also minimize backlash, which is when gears can rotate freely while meshing without turning the other gear. That can cause problems with accuracy and other sort of things, especially important when you're programming autonomous robots. Yeah, as I mentioned, you can have a custom number of gear ratio, so we can make whatever gear ratio we want, really. And you can have a custom distance, so you can have gears that perfectly mesh together. You're not constrained by having just store-bought gears from a kit. These are highly specialized, and they're also easily modified for iteration. So if you want to make another one, you can just make a new model and 3D print it, and you can iterate very rapidly with those. So as you can see, we use this in our claw model, or this is a version of our claw model for this year's robot. It's proven to be very helpful. Some cons. The first one is speed. These would not be great for like a chassis or a drivetrain, simply because they would be made out of plastic, and the plastic would wear out over time, and there'd be some backlash issues, or it might break after that. However, strength is sort of an issue, sometimes not. By default, these are very light, and the strength can be combated if you make the right geometry, you make the teeth the right size and all that, and you can get pretty strong gears. We actually use these gears to lift an entire whole arm on our bot, and it has no problem whatsoever. But they would not be as strong as a metal gear of the same shape. So let's start off this tutorial with the first step, which is getting the software you need. First thing you will need is a program called OpenSCAD. It is a parametric 3D modeling software. You can get it from this website by just looking up OpenSCAD. You download the package, install it. This is basically, you can make a program that creates 3D models for you. The next program you need is FreeCAD, which is a normal CAD editing software, but it has some cool features. It's, again, completely free. Both of them are free. It has some pretty cool features that we will use. And then the last thing is you need to get the .scad file, the actual code that runs in the OpenSCAD. You can get this from Thingiverse. If you just look up Parametric Herringbone Gears Thingiverse, it's one of the first things that shows up. You download this .scad file, and then you can get started. Next step is to actually generate these gears. So the first thing you'll do is you'll open up OpenSCAD. You'll open up the .scad file, Parametric Herringbone Gears.1, and you'll come to this screen. So the first thing it shows you is a pre-generated gear. It kind of showcases how this program works. It generates 2 gears of varying size depending on your parameters, and then you can generate each of those separately when you need to. But the first thing you'll see is line 11, generate equals 0. This just allows you to see both of the gears. We'll change that later when we figure out what we want. The next thing you want to look at is the distance between the axles. There's multiple parameters you need to look out for. First thing is the center distance, which is on line 16 here. Right now it sets to 60 millimeters. Let's say I wanted to do 50.8 or 2 inches. Then I can hit this 2 arrow button here, and it quickly renders me a new version of the gears. Then you have the gear height, or the thickness of the gear. This is helpful if you want to make a thicker gear. We'll have more mesh, be stronger. Thinner gears obviously are thinner, lighter, take up less space. Let's say I want this to be 8 millimeters. One of the other parameters is the gear shaft height. You don't have to worry about that one, really. That is the little nub that shows up on the end. Usually what we prefer to do is take out any of these basically mounting to axle options later on in the process, and we opt to use a metal collar or something like that, which tends to be stronger than a plastic collar. So you can either ignore this or zero it. The caution with zeroing it is sometimes if you zero a parameter, it'll generate the CAD or generate the model in a weird way, and you'll have to restart and regenerate. So I usually just leave them. It makes it a little more difficult to clean it up afterwards, but it's not that bad. Then you're going on to the gear options. It starts gear 1, gear 2. And this is where you get to enter in the teeth. This is the other parameter you get to look at. You can determine your gear ratio with these teeth. It's helpful to choose prime numbers, though, for these gear teeth. It just helps it generate correctly and make sure that they will mesh the right way. So let's say I wanted a just 1-to-1 gear ratio. I could do 2-to-1 or somewhere close to that. I think I'm going to go 2151 right now. 1951. Prime numbers there. So I want this to be my gear ratio. I can regenerate it. Wow, look at, I got cool gears. I'm actually looking at this right now, and this brings me up to a next point about how you want to balance basically the thickness of your teeth, and the thickness of your teeth, and that's determined basically by how many teeth you have and also the distance between them. But bigger pitch diameter or the bigger teeth. If you have them too big, they won't mesh super great. Because they'll be hitting each other, especially with the herringbone pattern, but too small and they won't mesh enough and they might slip. So right now I'm looking at it, it seems like it's a little too small. So I'm actually going to decrease both of these. I want it to be a 13 and I don't want 51. Instead, I'm going to go for 1319. Make them nice and clean there. So these are some pretty big teeth. I'm going to go 29 instead, just to make sure they're safe there. And that looks like a pretty reasonable gear. So you can look at basically the two sizes, the number of teeth in each gear. You also adjust the gear height, but you can also adjust the gear twist. All these other parameters are determining of like the motor shaft and these holes that are drilled in. You can edit those. I encourage you to explore as you look into it. There's a lot of customization you can do, but I'm going to ignore those for now. Like for example, gear cut circles, I could make that 0 if I wanted. But then if you scroll down here to line 84, you can see this teeth twist variable. That is another parameter you can look at. If you set that to 0, they would just look like normal gears. You wouldn't have that herringbone pattern, which sometimes you may want. But that herringbone pattern is really nice because again, that's where you get the aligning qualities and that's where you minimize that backlash. So I'm going to have that teeth twist go to 0.5. You have to look at basically your 3D printer and determine how much of an angle you can print. But you usually don't want more than 45, 50 degrees just for the quality of the print. But 0.5 is usually good enough. It twists enough that you'll have those benefits. So now that you have the two gears, you want to generate both of them. I'm going to just generate one for now. But in order to generate one or the other, you go back up to this generate line and hit either 1 for the first gear or 2. The first gear is usually the smallest one. It's the one without the cut circles. And now I want to generate that one. So I can hit the preview button again. Boom. It just shows that in the preview. Then I'm going to have to render this gear. Rendering process takes some time, but it'll render it. It'll make the whole STL file ready for you to download. Okay, so after you have generated the STL file, you're ready to go ahead and download it. So we'll just download it. I usually name it to name the number of teeth each gear has, the ratio it's designed for, and the distance between the axles, because those are the main parameters. But I'm just going to name it Herringbone Gears 1 for now. I seem to have a copy. I'll replace that. And once you download that, the next step is to bring it into FreeCAD so you can turn it into a step file and then later simplify into Onshape. If you don't want to do that and you just want to print it as is, then you can take it straight to your slicer. But I like to edit it so we can make it just what we need. So the first step you'll do once you open up FreeCAD is you'll open up the part menu. Then you will open up your newly generated STL file for your gear. You'll bring it in, it'll import. Then you'll make sure that you select the object. Make sure you select it every time you do a turn, basically. Then you'll select from the part menu to create a shape from the mesh. This will take some time. It'll ask you enter tolerance for the sewing shape. Just keep that at 1. It's kind of just like the detail. It usually works well for 1. But this process will take some time, but it will make sure that you have the right shape, and you'll be able to edit it in FreeCAD. If you want to save some time, you don't have to generate both gears. You can generate just the one and make a copy of the other one to have the same gears. This would only be an option, obviously, if you have the same gear ratio, same number of teeth you want for both. But otherwise, they would be basically identical. The one difference being one is flipped 180 degrees over so that they mesh properly. So keep that in mind if you're making mounting holes and such. All right, so once you generate that shape from a mesh, you'll select the newly generated shape, go to the part menu again, and create a refined shape copy. This refined shape copy will just clean it up a little bit, make it more simplified, and then you go to the part menu again for the last step, which is to convert to a solid. If you did everything right, you should be ending up with a verified solid, blue little check mark up here. Sometimes, though, if you generate the OpenSCAD thing wrong, or if you zero out holes or something like that, there might be some issues. Don't know exactly why this happens, but in that case, you would have to go back, change some parameters in your OpenSCAD, and then get back to this point. But after you have this solid, just make sure you select that solid, and then you can export it from FreeCAD as a step file. Yep. You save it as a step file, and then you're ready to bring into your own CAD software. And then for the last step, you will import that step file into your CAD software of choice. We use Onshape at 9.15 wrench dressing. Import it. It'll have to translate it real quick. After it's done translating, you'll open it up. Something that tends to happen is it imports in a very dark black color, and it's kind of hard to see the details when you do that, so I just go to the Appearance tab and change the color. This is probably different in other programs, but in Onshape, it's just like that. Change it to a lighter gray. Now we can see all the details we want. I like hiding that as well. So now we have our nice gear, but we don't want to have this big hub attached to the gear. We want just the gear, and then we want to drill in holes that will fit a normal Tetrix axle hub to make it fit with the gears that we need. So, and again, this is just one of the gears. We'll need to do this for a second one. So the first thing I do usually is get rid of the hub. I use the split tool. I select the face of one of the gears as my entity to split with, and that'll divide everything into 2 parts. And I will delete the extra one. Wonderful. And now I have a nice flat face. The other side looks good. This would be ready to print as is, but we do need through holes to have screws attach everything. So then I just quick make a sketch. I'm going to make this the size of a Tetrix hub and the size that the Tetrix hub can key into it as well, that little nub pilot hole it has. I think the holes is not 39. Oftentimes you will snap to being tangent to one of the lines on the teeth. You'll just have to remove that constraint in your sketching software. But I'm going to quick make a circular pattern. The circular pattern, I want 4 of these holes. 4 of these 3.9 millimeter holes, 8 millimeters from the center point with an 8.2 millimeter hole in the center. I make all these holes, and I've designed the gear in a way such that this inner side has plenty of room so I can make these through holes and won't go into any of the teeth of the gear. It's helpful you'll get a hang of that after a while. Make sure it's the right size. Can't make them too small. And then I'll just extrude these holes through. And now I have some nice through holes. If I wanted to, I could counterbore them, add some other features. And some of my gears, we've cut off the tops to make room. You can do a bunch of stuff. You can make a whole thing out of this gear, attach it to your whatever you need. But now you have a basic gear that you can use, and I know the exact distance everything is going to be, especially if we're using other 3D printed parts. I know these will mesh perfectly. and now you have custom gears that you can use.